Welcome to the course on FPGA based signal processing systems. We'll continue with the FSM modeling styles of Mealy machines today. Also, some of the timing controls will be learning. So, Verilog state machine modeling styles, we had in the previous lecture learned that there are 5 styles in which how do you combine these different blocks of important blocks of the Verilog state machines, the state memory, next state logic and the output logic, in which the styles of we have listed here 1 2 3 4 5, in which the three of the blocks, important blocks of state machine, are separately modeled in the sense 3 different always blocks in a module, and then it is style 1. If you combine all of them, it gets into the style 4 fashion, and combining this state memory and next state logic, or next state logic and output logic, or state memory and output logic, so the other block kept in the separate always block in 2 3 and 5 styles. So when we look at this for style 2, because style 1 we had already gone through in different sequence detector and Bailey machines. So the combine the state memory and next state logic for the style 2 state machine. In the Mealy, what is the difference we observe from the Moore and Mealy machine is that we have this input which is also deciding the output logic. Okay, so the considering the code which we had taken for the Moore machine, and we just modified it for this Mealy only according to the state diagram which we had used in the as a first example. So in this we have this 4 states A, B, C, D, and the states are moving, the state machine is moving from one state to another if there is enable input 1, or enable is enable 1 here and enable 1 here, and if it comes to D and it completes its all the states, and if it is not, then it's going to be staying over in that same state, and the output A, B, C, D will be the zeros. You can see that input and outputs are marked over here. So this state machine we have modeled in the Verilog. So state module, the state machine, clock, enable, output is Z and SREG. So as we declared that we are going to we are using in always block, these are going to store the variables. So it is declared as registers, Z and 2-bit register, because we have this 4 states. Next, to define the states, the 4 states, what are the A, B, C, D, using the parameter declaration. So 0 0 0 1 1 0 1 1. So as we did in the any other state machine. So after declaration, we combine the state memory and next state logic in this case. So we have always at the passage of the clock, the state memory, we have this case as reg, that is SREG. SREG is the current state here. Based on the state diagram, if the current state is at A, check for this enable input. If enable input is 0, then assign this SREG A only. So the next state of this SREG would all be A. Else move to the next state. So we have brought this state memory here using the non-blocking statement. If SREG at B, that is the current state is at B, enable is 0, then stay over there, otherwise move to C. So similarly at C, if enable is 0, stay over there, or else D. So here this it is given over here if this is C and the output is 0 and it stay over in the state. We have not considered this output here. We are just using the state memory and the next state logic combining the using this always block, and the output logic will be a separate always block. Here is D, the last state. If enable is 0, then stay over there, and else SREG is A. So default SREG is A. End case, because the default is mandatory, and need to end the case here and then end. After combining this next state logic and the state memory, so output logic comes into a picture. That output logic, what we do is always at the enable or SREG. You can see the thing here. I have put it in the different order to show that only the N, A, B, C, D. So, always at the rate enable or SREG. You can see that enable also is coming into the sensitivity list. If SREG is A, so the current state is A, then go to z equal to 0, else z equal to 0. So, because we have this at A, or it is moving from A also, the z is 0. Okay. So, at B again C and D, at only D z is 0, else it will be 0. It can be done with only one if else statement as well. So, considering this next state logic, you can even we can put SREG is A and enable can also be considered. Enable is 0, then z equal to 0. So, we can change over here with the that would also suffice because enable is included in the sensitivity list. If not, that this, because already this is satisfying this enable condition, so we neglected here to include this enable in the if condition. So, this separate output logic is separate always block, and next state logic also next state logic under the state memory or in the same always block. This is one style of the Mealy machine because the output logic sensitivity list includes that enable. So, if there is a change in enable, then it would be reflected in the output logic immediately and that would also be reflected in the current state after calculating the next excitation signal, and then it goes to the current state and then it gets replaced. So, but when the enable is changing, it's immediately getting reflected in the output logic with the current state available, but that enable would be reflected in current state in the next clock cycle, next passage of the clock. So, the style 3 in which we combine this combinational circuits, next state logic and the output logic in one always block and the state memory in the next one. Next always block. So, taking this same module, clock enable Z current state and the next state. From that we have Z SREG and then S next is also declared. So, it is up to us if it is X next is required, we can take them out S next also as an output. Next, declare this parameter A that is using the parameter states A, B, C, D. So, 0, 0, 0, 1, 1, 0, 1, 1. So, after that it comes to the always block in which the create state memory. So, the state memory is separate here. S next is assigned to SREG. So, the output logic and the next state logic which is combined over here is having this enable or SREG. So, you can see the sensitivity list which is taking enable and SREG both. If SREG the conditions, this go to the next assign this next S next is A and Z is 0. So, once this X next is assigned, then that would be going and updating the SREG. Okay, so that Z will be this is an after this is a sequential. So, it will be after assigning this Z is getting updated, so that this will be this also get the SREG. So, we have this else condition as well. What should be the next state B and output Z0. If enable is 0 at B, this is combining this output and the next state logic. You can see over here, if enable is 0 at C, next state is C and then Z is 0. So, similarly at D, if according to the state diagram, that is it goes to next state A and Z is 1. Default is S next is A and Z equal to 0 in case N and N module. So, here the combination of this next state and the output logic can be seen, which uses the blocking statement preferable for the combinational logics. State memory is created separately. So, this is the example of style 3 merely, and style 4 which combines all of them, that is the state memory, next state logic and output logic here, which includes the passage of the clock as well as the combinational circuits. So, taking the module is clock enable Z and SREG. We have this declared them the SREG, that is the fourth style, in which we have same as current state is 2 bits, and declare the states, what are the states, as we did in the other styles as well. At passage of the clock, now we combine these three three SM, NL and OL. Always at passage of the clock, begin that SREG is A. So here the current state is updated, and you can see this otherwise SREG is B. So get this SREG, yes, this is including the state memory condition, that is assign this A to SREG, B to SREG, and similarly in other states as well. See what we have done in the previous cases. Blocking assignments would also work. When you combine this, we will not be able to give the use the non-blocking statement, then the update, because within the within one always block, if you will not be able to combine this non-blocking and blocking assignments, so it's not there we will get this indeterminate results. So then use this blocking, then once this state memory thing is done, so and the next state logic is also assigned here, we'll go into the output logic, in which, so after completing this default state end case, so comes the output logic within the same always block. If enable is 0 and SREG is A, then Z is 0. If else, if check this condition of enable and the current state, both Z equal to 0. So current state and the enable input is checked, or enable 0 and SREG. So after assigning the current state here SREG, you can see enable SREG is getting updated first in the always block, because it is sequential. Once the case SREG is met, then it goes to the particular current state and check this current state updation. After updating this, it comes to the if else block of the output logic, and then check for the enable as well as the SREG and else if. So here is enable 1 C, which has the only last one, D has the 1, otherwise becomes 0. So else if, so in enable 1 it goes to A, else Z equal to 0. So fulfill the condition of else also, and end. So this block is put inside the always block after completing the next state logic and the state memory. Output logic is also combined to make it sequential in this. So this is for this is style 4 merely. And then style 5 merely machine, which is combining state memory and output logic. Next state logic is different always block. So the same module declaration continues here with the defining states as well with 2 bits. After that, we here out state memory and output logic. We have this just to declare this SREG here. SREG is something the current state, which is getting the S next from the next state logic. So the next state logic is going to be in the some other always block. So that would be a separate one. Here we see that always at passage of the clock, this is constituting the state memory, whereas the output logic, if SREG is enable 0, Z 0 and else Z 0. So the output logic is made into the same always block. Once this SREG is updated, then it gets into the output logic, whereas S next is getting this at passage of the clock. This is having the output logic with the D also. D is 0, D Z is 0 if enable is 0, else it is going to be 1. And default end case, N, this is completing the output logic, and the first statement gives the state memory. So after this, that S next, the first statement in the previous always block is getting the next state from here. You can see that the enable or SREG. how this SREG is, you can see the enable also is placed over in this finding the next. S next is getting in A, else it will get S next will become B. So this is giving the next state logic separately. This always block, putting all the conditions once again. With this, this is one always block which has all the next state conditions similar to the first previous cases. So then can notice this, it has the enable as well, next state logic and end case. So this is N module with the style, which is the output logic and the state memory. The next state logic is separate one. So with this we would be we were completing that all the cases of the style, how different styles can be made in the finite state machines. Especially we look at the style 1, 2, 3, 4, 5 just to optimize the code with one always block. And if it is also good to have this 2, 3 always blocks, but you have the always blocks are if you have multiple always block, those are concurrent, and inside the always block the statements are executed sequentially. So that needs to be taken care. So if you have the one always block, it is easy to have it is the code minimization as well as the sequential execution can be made in that same. Sometimes it is having 3 always block would be better to have the combinational logic or okay. So sequential logic separately. So sequential logic separate always block and combinational logic can be in one always block in a particular digital circuit. So this is giving the more way of coding the finite state machine in different styles. The Verilog modules can be made. So the equivalent realization, the hardware equivalent of these codes we will be doing, and the synthesis processes we completed. So when we do the synthesis, we'll synthesize these codes and see that how this realization is exactly getting into the hardware components. So next we will be moving on to the timing controls of the Verilog. In this case, this various behavioral timing control structures are available in the Verilog. So behavioral timing control constructs are usually used in this simulation. So if it is these statements are actually helping the simulator to find to advance actually one time to another. So if there is no timing control statements, there won't be any simulation time advancement. So then it provides this which simulation time, what's the procedural statement should be executed. Okay, it specifies this time at which it should be executed. So you have this 0 nanoseconds, 5 nanoseconds, 10 nanoseconds. The simulator looks at this timing controls at 5 nanoseconds, what is the statement to be executed. So it specifies the way to specify the simulation time to how this Verilog constructs to be executed. So if we classify these timing controls, which we use it in the procedural statements, one is delay based timing control. So we are using them, delay based timing control, and we will be now recognizing what is the delay based timing control and which one is the event based timing control, the second category. Also the third one is level sensitive timing control. All of them we are anyway using in our examples so far, but we will be this is now we'll be able to recognize that in the code that what is the delay, which one is delay based, which one is event based or level sensitive. In the delay based timing control, we have again 3 types: regular delay control, intra assignment, and the zero delay control. So these 3 types we will discuss in this lecture. Also the event based will be again having the regular event, named event, and event R control. So the sub classifications and also will be discussing with examples. So coming to the delay based here, It can be specified with a number, identifier, or a expression, or it can be a min-max type expression also. So usually that is so we are using the delays are specified with a symbol hashtag. Following the hashtag, it can be a number or some logical expression, or min-max type expressions can be used in this delay based. So the first category is that regular delay control. So in all these controls, we will be using that hashtag. So regular delay control, it is a time based one. So which has this non-zero number, the delay is specified with the to the left hand side of the procedural assignment. So let's see that we have some examples. Suppose the parameter declaration we had learnt, the latency is a variable which is assigned value 20 in this example, and delta is giving 2. So define some registers like X, Y, Z, P, Q. It's not a normal, it's a piece of the piece of code which helps to understand the what is regular delay control. Okay, so we have given that latency delta and X, Y, Z, P, Q, there are registers. Initial begin X is 0. So X equal to 0, it is obvious that there is no delay specified. So X is assigned 0 value at time t is equal to 0. Hash 10, you can see hashtag 10, y equal to 1. Yes, there is a, in the left hand side of the procedural statement, there is a hash 10. This we use it in the case of the test benches. All the testing of test benches, we used to give this time control, if you recall. So this is executing this statement y equal to 1. The y will be given value 1 after 10 time units. Okay, the execution itself is delayed here, so it's a delayed evaluation. Okay, and then hash latency, it's a regular delay. Latency is given 20 in the previous slide, that is 20. We have using the parameter we declare that is it latency is going to be after 20 is that is 0. So the latency can be an here identifier, the delay of 20. Instead of having simply the number, you can use this latency identifier as well. So in the other case, that is latency plus delta, you can use the expression of adding 20 plus 2, delta was defined as 2, p equal to 1, 22 time units, this expression assign p equal to 1. Hash y is now getting that 1 value, 1, x equal to x plus 1. So take this y value, you can have this y also after the hashtag. So that is possible to have this identifiers also in the regular time delay control. Other one could be noticed that when it is used normally in the gate delay modelings, hash 456 colon in between q equal to 0, that with this which specifies here for this is the minimum, and 4 is minimum, 6 is maximum, and 5 is typical value. So which one will be chosen, that is in the gate level model, it describes the 3. So it will be in the gate level model, it will now when we do that, this will be discussing that what is which one 4, 5, 6 out of which is typically it will be using the delay of 5. Minimum it should be at least 4, or maximum it should be 6 to execute this q value. So the delay values can be used. So this is for a piece of code which describes the regular delay control. Not only the number, identifier, expressions could be min-max type expressions also can be used for defining the timing controls. So it is delayed, the execution of this assignment is delayed by the number whatever is specified after the hash. So the intra assignment delay control, that is also the instead of regular one. So we have this, it is specified to the instead of specifying it to the left hand side like in the regular delay control, it is specified in the right hand side of the assignment operator. So for example, we have xyz, the shall begin x equal to 0 is 0. You can see y hash 5 we have used in some of the examples with the non-blocking statement x plus z. So here take the value of x z at time t equal to 0, that needs to be noted. It is #5, it is not evaluation is delayed, it is assignment is delayed in this case. So, whereas in the previous case, if you put this over here, the whole evaluation x plus z is evaluated after 5 time units. So, whereas in x and z are taking the 0 values, what is at time t equal to 0, and wait for some time, and after 5 time units it get assigned in the left hand side y. So, time 0 evaluate it and then wait for 5 time units and then assign to y. So, that is intra assignment delay, that is taking time for the assignment. Similarly, the x equal to 0, it is equivalent to saying x is 0, z 0, evaluate that at x plus z and store it in a temporary variable, and then use that temporary variable after 5 time units to assign it. So, it is equivalent to the regular delay control with the temporary storage or temporary register which has temp x is set. So, though this x and z, here the point to be noted in the intra assignment delay, once this is at time t equal to 0, x plus z is computed and then it is assigned to y after 5 time units. If in between after 0 and 5, if x and z changes, the value changes, it will not be reflected in y, okay, because the value which is evaluated at time t equal to 0 will be assigned after 5, okay. So, that will be neglected. So, after assigning, it looks for, suppose it is a continuous process, it looks for the current time, what is x and z value, evaluate it and wait for 5 more time units and then assign to left hand side. So, that the x and z might change in between, that will not be reflected in the y. So, it does not affect y in that sense. Suppose the glitches which is happening in between in the signal, so the time equal to 0 and if it is put 5, that will be ignored in y. So, that is intra assignment delay. See, note the difference, regular delays defer the execution of entire assignment, that is after the time delay only it looks at the value, evaluate and then that is a delayed evaluation. Intra assignment evaluates it and then taking time to assign, that is the whatever the value time delay which is specified, that is the difference between these two. So, it is also the temporary variable which is to be equivalent in the intra assignment delay, as I said in the previous case. So, zero delay control, in which the third category of the delay based timing control, wherein x 0 y 0, suppose in initial statement, you know, initial is executed only once, and which is within the initial block you have the sequential execution, x 0 y 0 is getting assigned. What is initial begin? If you put #0, it is very interesting that #0 y equal x equal to 1 y equal to 1, what happens here? It is also there is no delay. So, once this it looks at the hashtag and wait for this execution, it is a number of 0 or not, it is waiting for that time, it wait little bit. So, x and y, x is getting 0, y and 0, time t equal to 0, but within this always block, if you put multiple statements #0 and #0 here, x equal to 1 y is equal to 1, which one will be executed first will be a indeterminate one, but it will be executed last after x 0 y 0, x equal to 1 or y equal to 1, or y equal to 1 x equal to 1 will be updated. So, this is zero delay control. It is a delay based one, instead of having the number or expression or anything, just keeping this one to be executed little later than this. So, we can have the 0 hashtag 0. So, there are four statements, x 0 y 0 x 1 y 1, as I said, it should be executed at time t equal to 0. However, x 1 y 1 have this, so it will be executed last in time t equal to 0, and the order in which this x and y will be executed is not deterministic one. So, if you have this to have the initial blocks are the always block, that is maybe in that procedural statements we evaluated at the same time, because those are concurrent. If you have two initial block or two always block, it will be concurrent. The way in which it is executed is again the different ways in which this may be evaluated, but at the same time the order of execution in this is non-deterministic. That is why different always block the order. If it is sequential and depends on the time delays used in the statements. Zero delay control, at least it makes sure that it is going to, that treatment is going to be executed at the last in the 0 time, t equal to 0 time, if you make this. But the order in which, if you have multiple statements of 0 delay, it is not deterministic to say that which one will be executed first. So with that, we kind of say that 3 types of delay controls. Those are the delay based ones are 3 types that we had seen, and other 2 types of the timing controls we would see in the next lecture. Moreover, this timing controls helps in advancing the simulation time. With this blocking, non-blocking, and then sequential and concurrent one, of these with this timing controls, also it is delayed evaluation or delayed assignment. Those things will be covered in the next lecture. Thank you.